Hey, everyone in Zoom. Can you hear me? Okay, good. Let's try this screen share thing. It worked well without any problem the other day and yesterday as well. So let me see. Share content screen, microphone on, start broadcast. 3, 2, 1, and broadcasting. And can you see the screen? And right now I can't see your chat, so please, tell me whether you see the screen or not.
I can see it.
I can see it.
Okay, so you can see it, right?
Yes.
Yes.
Okay, awesome. Huh, I really don't understand what happened last time, but so let's see. Okay, so let's get started. Last time we started talking about this instantaneous center of zero velocity, and this is a slightly different concept than what we have been doing. So from here and there, we start to talking about this rotation, and by considering that, we need to find when you're looking at the velocity at point or the acceleration at points on top of a rigid body, then you need to start considering the rotation. And the ways you approach this is by using some absolute motion analysis, or using this relative motion. And this thing, it came up in order to, make the analysis a little bit more easier. But still, this method, you need to do the vector product, like the cross product, to find the actual movements. And that really helps us to solve all the problems. But some smart people came up with a new concept that is called instantaneous center of zero velocity. And by using that concept, you will be able to approach problems more intuitively, and also you don't really need to go through that vector products, but it can be approached more in like a scalar computation way, okay? And the thing here is this instantaneous center is, like, for example, for any rigid body motion that is on a plane, there is this point that has instantaneously zero velocity. Like, for example, if you see this bicycle wheel moving, this picture was taken, at a shot, and you can clearly see this part here. And though the picture is clearer compared to this part, because here is blurry because this guy is moving, right? But this part, the reason why it's more crisp compared to here is it has instantaneously zero velocity. This point here is not moving at all at that short moment, okay? So that happens for all materials, all rigid bodies. So we wanted to use that thing. And the way you find the instantaneous center is the property of the velocity with respect to the IC, or the instantaneous center, is the velocity of that particle is perpendicular to the vector you pull out from the instantaneous center to that point. So by using that property, if you just know the velocity of each particle here and there, then you draw a line that is perpendicular to velocity at each point. And if you find the intersection of those lines, then that is going to be your instantaneous center. So with respect to this point here, this rigid body is rotating for that just moment, okay? And this instantaneous center is going to be continuously changing in general. So this is, by its definition, it's an instantaneous center, okay? And by using that, we will be able to make the analysis much simpler. And let's just try some examples to see how this works, okay? So we dealt with this problem previously, I believe so, right? We did that here, and in order to do that, you have to define the XY coordinate system and all these values, and do the vector product to finally get your answer, right? And let's see how this can be simplified. I'm not saying that the previous thing that we did is not important. That is also very, very important, because in some cases it's really hard to find this instantaneous center of zero velocity, like, intuitively. So in some cases you may need to really go through the hard path, but yeah. So this finding this instantaneous center is more like an intuitive thing. So you will need to have like a good sense of what's happening right now in this system, okay? But if you have that kind of good feeling, this is going to save you a lot of time. So what's happening here is this bar is kind of it's falling down and it's moving like that, right? So this part is gonna move like that. And this part here is gonna just roll down vertically, right? So we can identify the velocity at this point is going downward, and the velocity at this point is going towards the right. So we can easily find the instantaneous center by extending a line that is perpendicular to a velocity at one point, and to another point, the velocity is like that. So we find, we draw a line that is perpendicular to the velocity at the other point, okay? And then suddenly there's going to be a cross-section point, and that is going to be our instantaneous center. And at this moment, we can think as if this rigid body or the bar is rotating with respect to this point, just for this short amount of time, okay? So we can write down first. Velocities on each point, then find the IC, by drawing these lines perpendicular to those velocities. And then back again. Identify each point. So first, what I mean by this find the velocities in each point is you just find how this is going to move. And then you will be able to find the instantaneous center. And then by using this information, you will be able to determine the actual properties. Like this is like 5 meters per second, and this is 3 meters per second, etc., something like that. So VA is going to be omega cross RA, and VB is going to be omega cross RB. And this is from your instantaneous center. See? So you can think this thing is rotating with respect to this instantaneous center. So velocity at this point here is nothing but omega times r. This is your omega, and this is your r, right? Because if you have a structure that has an axis of rotation and it's here, it's rotating like that, then the velocity is what? That's the velocity. And the way you find it is from the center of rotation, you just multiply omega times r, right? So we're doing that thing here. So this is the rigid body, and that guy is rotating like that. So the velocity at this point here is omega, let's write it down, omega times the vector r, right? And the velocity at this point here is omega times velocity on the vector r. Okay. So if we start with VA, VA is what? It's 3 meters per second, right? And that is going to be omega cross omega times RA. So it's going to be omega times omega. We don't know that, right? Yet. And then R is the distance from here to there, which is going to be, this guy is 1.5 and this is 30-degree angle. So this distance is sine, right? So 1.5 sine 30. So by solving this equation here, we can find, hey, omega, that instantaneous rotation velocity, angular velocity, omega, is 4 radian per second. And because this is a positive value, it is just following the direction we have. So it's going to rotate like that. And now we can utilize this value, put it here to find VB, which is our question here. We want to find the velocity at this point there. So VB is nothing but omega times RB from the instantaneous center. And that is 4 times what? The length here is 1.5 cosine, right? So it's 1.5 cosine 30. Right? So we will be able to find this is going to be about 5.2 meter per second. And we know the velocity is going down, so it's going down like that. Okay? Okay. So let's just move on to, try some other examples, and hopefully those examples help on this understanding this concept. And the next example here asks us, what's the angular velocity of rod AB and BD? So this is AB and this is BD. So it's the velocity at this point D is provided, that's 3 meters per second moving towards the right. And at this instant, it is 45, and this is 45, and this is perpendicular. Okay, so it's asking what is the angular velocity of this guy and the angular velocity of that guy. So we can first define the angular velocity of each point like this, or let's just draw this thing down separately. Like that, okay? So here is A, and this point is B, and this is omega A, okay? And at that instance, this is 45 degrees. So, excuse me. So from here, we can clearly see, ignore this part right now. We just consider this part. And what's what's going to be the velocity of this point B? It's going to be pointing that direction, right? Because this beam, this rod is rotating with respect to this point. So you can easily imagine this is going to be the velocity of point B, right? So that's VB. And VB is what? It's omega cross R like that. Let's just keep all the subscripts just to make things clear. Like this. And well, here we don't need to really go through this cross product because we know that the velocity is going to point down like that. And we can just say this is omega A times RAB is, the length of this guy is 0.4. Okay. So we know this is going to go down like that, but unfortunately, we don't know what omega A is. Right? So how about we go to this part? And because we know what's going on here, probably we will we will be able to go back to find what this VB is based on the knowledge from here. So let's see if that happens. So if we draw the other part, say like this, we have like that. And this is 45-degree angle as well. And this is D, and this guy is our B. And from here, we know that we don't know how fast this velocity is because we don't know the rotation velocity, angular velocity, but we know that it's going to point towards this direction, perpendicular to this rod. So that means it's a 45-degree velocity. So we can just use that information here. This is going to be VB, okay? And we know from the problem, it says velocity of point D, let's just plot it here, is going to point like that direction. And this is given, it's 3 meters per second, right? So if we just take a look at this guy, we will be able to find out the instantaneous center of rotation by extending a line like this, perpendicular, and a line like that, perpendicular. And here may be the IC of this particle, this rigid body. Okay, and if we call this guy as RB, and let's just call this guy as RD. The length is RB and this is RD, okay? So we can clearly find that RB has a length of what? This is 0.4. And the angle here is 45. So this is perpendicular. That means this is 45 too. So the length here and there should be the same, right? So that's 0.4 meter. And RD should be what? We know that this is 0.4 and this is 45-degree angle. So can use cosine or sine theta of 45 to find the length, and that should be 0.566 meter, like that. So we know the length of these, and unfortunately we don't know the angular velocity, but we can just easily, call that thing, define that thing of our choice. And that's actually what this problem is asking for. What's the angular velocity of this rod and that rod, right? So we can just assume the angular velocity is like that. And let's call it omega BD. Okay. So the velocity VB is going to be nothing but omega BD times RB, and the velocity of VD is going to be omega BD times RC. You get this here? This guy is instantaneously rotating around this instantaneous center of rotation. Okay? So this point is nothing but the velocity of that point is R times omega, and the velocity of this point is nothing but R times omega. Just like we got it here. We're not really caring about the angle and the direction at this point. We're just looking at the, the magnitude of the velocity, right? And this guy is given to be 3 meters per second. So if we oopsie, this is not C, this is D, right? So if we utilize this information in here, we will be able to find omega BD, isn't it so? So omega BD is going to be RD divided by, VD divided by RD, right? VD divided by RD, and that's 3 divided by what? 0.566. So we know that omega is 5.3 radian per second. And because this guy is a positive value, right? So it is going to rotate along the direction we define like that. So it's going to rotate like this. So we just write it that. This is the rotation direction. And from here, we can also know VB. This guy VB is what? It's omega times RB. And we know that RB thing here, right? So VB is, omega is 5.3 times RB is 0.4 from this one, right? And that's going to turn out to be 2.12 meter per second. And since this is also a positive value, it's just going to follow the direction you defined. If this were a negative value, then it's going to have a velocity in the opposite direction of what you define, right? So it's important that you define the velocities, directions. It really doesn't matter whether it's going to be on the right or left. It's just of your choice. And if after you just follow the direction you define and do the math, and if it's a positive value, that means it's the movement is actually going to be along the direction you defined. But if this is a negative value, then it's just going to be the opposite direction. That's it. Okay. But for this case, we know the velocity is going to point that direction, and it became a positive value. So we're just using that as is. So this is velocity pointing downwards like that. So are we done? Let's take a look. It's asking us about the angular velocity of AB and BD, right? So we got this BD. Okay, we're fine with this. What about that guy? It's this one here. And now we know what VB is, right? So we know this, we know that. This can be an easy peasy thing to find out, right? So (2.12) equals omega A times 0.4. So omega A is what? 5.3 radian per second. And this guy is also a positive value, right? So it's just going to follow the direction we define. So it's going to be a rotation like that. Okay. So we can very easily find, without doing the vector calculus, vector those cross products to do all the, to find all the, you know, components in X, Y direction. But if you have a little bit of intuition how this is going to behave, the intuition I mean is you think about, oh, this point B is going to move like that, and we can just define a rotation angle, angular velocity like this. And if you dissect this problem into two parts here and there, and you utilize the information you found from here to there, and this velocity is just given. So by using these two, you will be able to find the instantaneous center of rotation, right? So if you use those intuitions to find these in IC, then you'll be able to just you know, do the math in a more like a simplified way to find out all the information that is needed. Okay, so this is also a very clever way to approach some problems, but again, you still need to understand how to go with this kind of formal analysis, because by using this formal analysis of, you know, using I, J, K to find all the values, this one, even though a very complicated system you have, still you will be able to find it. And even some cases you don't have like a good understanding what's going to happen. Say you have a very complicated system, and then you can't really guesstimate how that's going to work out, right? So in that case, you will want to approach in this way to, you know, move step by step, and these numbers are not going to give you like a wrong answer, because it's just number doesn't lie, right? But if you have a good intuition of what's going to happen, probably you will be able to apply those knowledges to find this instantaneous center of rotation, and then the you know, the math is going to be a little bit easier. Okay, but for this one, you need to have a good sense of you know, engineering intuition. Any questions you have so far? Okay, let's try another example here. So we have a gear on a rack like that, and it's moving towards the right with 6 meters per second. Okay, and that means the velocity of this point here is 6 meters per second as well, because this is just a rigid body, right? And it's asking us to find the velocity of point A of the outer gear. So we want to find the velocity of this point here. Okay, so if we do that step one more time, just we need to find the IC. And of course, in order to find the IC, you need to have a good sense of how the velocity is going to move like, right? And then you determine the velocity in each point. Each point. Okay, so in this case, we can think this here is going to be our instantaneous, you know, the center of rotation, just like we found out from this here, because this part is instantaneously has a 0 velocity. So everything is rotating around this part, right? So for this system here, the outer gear is just rotating, but this inner gear is, rotating with respect to this part, right? And because it has gears, so there's not going to be any slip, right? So this is going to be our instantaneous center of rotation or zero velocity. So with respect to this point, your velocities are going to be this. Well, because of the color, what would be a better color to use? Maybe this one. That's the relative vector, position vector, and you're going to have a velocity that is perpendicular to that, right? This is velocity of A, right? And if you focus on the other part here, that's the relative vector, and this is going to be the instantaneous velocity. That's VO. Make sense? So if we just write those down here, VA is omega cross product RA from the IC, right? And VO is going to be omega cross product RO from the IC, right? So let's see, what do we have here? We know what VO is. That's 6 meters per second, right? And we will be able to also find the length of this guy. Isn't it so? Because it says the outer radius is 0.6 and the inner radius was 0.3. So this is nothing but 0.3, isn't it? So if we use this part, that is 6 meters per second is omega times this length, which is 0.3. So we will be able to find omega is 20 radian per second. And we didn't define the rotation angle, but it's going to be like that because it's obvious it's moving like this, right? So let's just have that rotation definition. So this is going to be our definition of omega. So our omega is a positive value, right? So it's just following the direction we defined. So that's going to be this one. Right? And then by using this information, omega, we now know omega, and we now know what? We can find this thing. And if we know that guy, then we will be able to determine what this VA is. So if we write that down here, VA is omega cross product RA over IC, right? And omega is, we define the rotation of angle that direction. So if you curl your fingers around in this direction, then your thumb is going inward toward the page, right? So your omega is a negative 20K, see, with respect to the direction of K. We always assume X and Y, and your K direction is pointing outwards, right? So this omega, we define this to be our omega, and that direction is actually going into this page. So it's a negative 20K. Cross product. And what's RA? So from here to there, it's going to be negative something I plus positive something J. So this is nothing but 0.3, and this length is actually 0.6, right? So it's going to be negative 0.6 I plus positive 0.3 J, right? If you decompose this position vector, this is 0.6 and that's 0.3. And this one is pointing towards the left, so it's negative I, right? So now if we do this cross product, I, J, K, and then our omega is what? 0, 0, 20, negative 20, and then this guy is negative 0.6, 0.3, 0. And if we do this one more time, this times the determinant of this. So the determinant of here is 0 times 0 minus 0.3 times negative 20. So it's going to be 0 minus 0.3 times negative 20. A lot of parentheses. That's I. And J is what? You find the determinant of that, which is 0 times 0 minus 0.6 times 20. So, but make sure you have a negative J, right? So it's going to be 0 minus 0.6 minus 20. J. And actually there's 0K because, you know, K times the determinant of this guy, and that's 0 times something minus 0 times something. So this just goes away. And if you do the math, that is going to be 6I, right? Negative, negative, positive, this is 6. And we have 4 minuses, so it's a positive value, J. Alrighty, so we just found VA is 6I plus 12J. And that is this vector. And you can clearly see, hey, this is 6 and this is 12. So if I just draw that down again, 6, 12, and that is your VA. So the magnitude of VA should be 6 squared plus 12 squared, and that is going to be 13.4 meter per second. And if you want to find the angle as well, tangent theta is 12 over 6, right? So theta, it can be found as about 63-degree angle, pointing like that. Okay. So by using this instantaneous center of rotation, you will be able to, you know, find VA, and well, here we're going to find VA, but by using this information, you can go towards where you want to find out, right? And this one here too. We know the velocities at each point, and from there we find the instantaneous center. Then you use that information. Okay. Any questions? Alrighty, then let's try another example. And let's try to finish this in time. Okay. Hopefully we will be able to. So this one here is asking us to find the angular velocity of rod AB and BC. So what system we have here is we have a link like that, and this guy is rotating 4 radian per second. And we would like to find how this and that guy are rotating. So we can maybe just assume these are rotating, you know, like this. Okay, so how I may do is we know this part here. So from this part only, we will be able to find the velocity. And from here, I would just propagate my understandings. And this one here is also an easy hint as well, because it's a fixed point and it's just a rotation. So we will be able to find the velocity of VB. And this one at the middle is a little bit like complicated thing, because it's affected by this motion and that motion. So it's going to rotate like this, and it's going to also translate moving up and down, right? So we might propagate what we find out from here, and then this one also gives an easy analysis point. So we will try to gather the information towards this center like link, and we'll see. Okay, so let's first try to understand what's happening in this point. So that particle, that body is something like this, right? And this is D, and this guy is C. And it has an angular rotation of omega equals 4, right? And we can clearly understand velocity of point C is going to be a horizontal velocity, right? Of VC. So from here, it's easy to find out VC is omega times R of, let's call it CD. And omega is 4, and R is, what's the length? It's 0.5, right? So it's 0.5. That gives us 2 meters per second, and we intuitively know it's going to point towards the left, right? Because this rod is, you know, it's just rotating like that. So this is the velocity. Okay. If you don't have that kind of physical intuition, then you will need to go through all the vector product, right? So omega is rotating like that. So that means if you curl your fingers towards this direction, your omega is, your thumb is pointing out of this plane. So it's going to be omega k hat, and with a positive value, cross product. R CD is what? It's 0.5 J, right? So you need to do the this product using that IJK, this thing. But if you just have that kind of physical intuition, you will be able to find this value like that easily, right? And we know this part is moving like this. Okay, how about we take a look at that one? And this guy is looking like that, and it's A and B, and we don't know how fast this is rotating. That's actually what's the question is asking us for. So we can just define that, hey, it's rotating like that. Let's just assume that that's omega A, okay? And from here, we can identify, we can understand, oh, the velocity is going to be like this, perpendicular, right? So it said it's 30-degree angle here. So that's one information we can keep. And VB is what? It's omega A time cross product RAB. And if we just do this, omega A keep it as is, and the length of that guy was what? It's 1 meter. So it's just times 1. So it's just omega A, right? Okay, so let's just keep this as is here. And for this particle, if we move on to that, so that particle looks like this here. And this is C, and this is B, okay? And from the link over there, we identify, we don't know the magnitude yet, but we know at least the direction of this guy, which is pointing downwards like that, right? This is VB. And we know the velocity of this point here, yes, that is going to be moving like that. That's VC. So we will be able to find the instantaneous center of rotation by doing something like this. This looks more like a perpendicular thing, right? So these two are perpendicular and this is perpendicular. Okay, so the intersection here is going to be our IC. Right? And then what we need to do, we need to, from here we can define VB is, let's call it RA, this is RB from IC, and this is RC from IC. I mean, this length and that vector here, right? And we know these are going that way, so there's a rotation angle velocity like that, angular velocity. So we define the angular velocity like that, and that's omega BC, right? So VB, this one is omega cross product this length, right? Cross product RB of IC. And the velocity here is what? It's omega cross product this length, right? BC is cross product RC by C. So we can start from using the information we know. We know this VC is 2 meters per second, right? And we could probably understand what this RC value is. So from there, we will be able to find omega BC. So let's try. So this is 2 meters per second, and I don't know what that omega BC is, but I know the length of this guy because this is said to be 0.4 meters, right? And the angle here is 30 degrees. So tangent theta is this length, right? That's 0.4 tangent 30. So if you do the math, that means omega BC is 8.66 radian per second. And because it's a positive value, it follows the direction we define. So it's going to have a rotation like that. And because we know this information, we can apply that to here to find this VB. So VB is going to be omega BC, which is 8.66 times RB, this length. This is 30-degree angle, right? And we know that it's a cosine, so it's going to be 0.4 divided by cosine 30. And that is going to give us, this is 4 meters per second. And because it's a positive value, it's going to just follow our convention. We define it's going to go like that, right? So we know VB is like this. So we found out VB, we can just apply that to here, right? So VB was 4 meters per second. That is omega A times 1. So omega A is also 4 radian per second. And this guy also has a positive value, right? So it's going to just follow the sign convention we defined. So it's going to rotate like that. Okay. So if you find the two velocities of 2 points, 2 or more points from a rigid body, then you will be able to, draw a straight line out of it, a perpendicular line out of those points, and then find the intersection to get the instantaneous center of rotation. And by using that, you will be able to define each velocity very easily and use those information to backtrack to your other parts to find what's going on in the system. Okay, so I hope this really helped. And so there was a homework assigned by next Friday. And we're going to have our next quiz on Friday as well. Okay, so solving this homework is going to be helpful for you to preparing the quiz. Okay. Do you have any questions about any homeworks or quizzes? Okay, if not, that's it for today. Thank you all for coming in and have a great weekend, and I'll see you guys next week. Okay.